Refresher on the principle of relativity. Galileo, using one of the fastest means of transportation available to him, made a thought experiment about sailing ships and how physics tends to stay the same even if you are on a fast-moving ship. For example, you and your crewmates can play a game of cards inside the cabin of a ship while you sail at its top velocity. And the cards remain on the table, omitting any sloshing. However, to people that can see you playing cards from the shore, the cards, say as you fold your hand, dropping the cards straight down, appears to move at great speeds from where they used to be to meters away in the direction of the ship's movement. What appears to you as the cards falling straight down appears to people on the shore like you tossed them across the sea such that they landed where the table will be, not where the table was. Galileo summated that the laws of physics hold good for objects in constant motion, that the motion is relative, that to the crew on the ship, the people on shore are moving, and those people on shore say the people on the ship are moving, and aliens watching the Earth floating past think that both of you are moving. There is no universal stationary object which all other objects are judged against. There is no center or stationary. Everything is stationary to their own perspective, and everything else appears to be in motion or stationary according to their stationary position. Einstein's special case of the principle of relativity is no different from Galileo's in principle, namely that Einstein's two postulates fall in line with the essential nature of the original principle. The first postulate states, physics is the same for all observers, just as Galileo showed. The second postulate is actually a derivative of the first, being that it states, the speed of light is the same for all observers. The second postulate comes from the first postulate, and from the work of James Bradley and James Clerk Maxwell. Bradley first found that the speed of light was the same no matter what star he measured. No matter which direction the Earth was moving, light was always the same speed. Maxwell showed that the speed at which the electric field interacts with the magnetic field is identical to the speed of light. Einstein, through his work, which we will explore here today, tied the two together and stated that the physics that is the same for everyone is a physics which uses light to interact, and therefore, no matter how fast or motionless you are, if you exist, then light is moving at the same speed as it always is. For physics to be the same on a train which is moving at its top velocity on Earth, or a lab on Earth which is spinning and orbiting the Sun, or a lab which is stationary in the Sun's frame of reference, which is orbiting the Milky Way's center, then the speed at which these atoms interact, the speed at which the atoms of brain neurons must interact, must be the same for all observers. For this, Einstein needed to show that 1. Photons are light, and photons interact with material as packets of wave energy. 2. That material which the photon interacts with are made of atoms, that atoms exist. 3. That Maxwell has a Galilean relativity problem, and that problem is solved by understanding what must physically be observed by people outside the moving frame of reference. And 4. That mass and energy are equivalent, which is the consequence of 3. All of which Einstein achieved in 1905 at the age of 27. The first paper was on what is called the photoelectric effect, which establishes that light comes in wave packets called photons, and that the energy of a photon is quantized. Newton, 300 years earlier, showed that light was heating up objects, not just shining light and color. That materials absorb light and reflect color and heat. Einstein showed that the absorption of light at certain frequencies could cause the material to emit electrons. Before Einstein's photoelectric effect experiment, scientists in electromagnetism thought that electrons could be emitted through a continuous buildup of continuous light waves, such that the material would continue to absorb energy until it filled up to a limit, and would then emit the electron. The experiment proved that this is not the case. Light of a certain frequency, which is lower than the threshold for the emission of the electron, never emits the electron, no matter how long you wait or the intensity of the light. However, a low-intensity, short burst of light at the correct frequency can emit an electron. Einstein thus showed that the best description of a photon is that it is a discrete packet of energy, a quanta of energy, not a continuous wave through space. This we will come back to when we get into quantum mechanics in later videos. In the second paper, Einstein modeled Robert Brown's pollen in water observations to show that the random motion of the pollen was caused by atomic interactions of water molecules, which at various times, interacting in various ways, interacts with the pollen in different places, in different degrees, and the resulting atomic forces physically move the pollen, resulting in what appears as the pollen randomly walking around the petri dish. The third paper, Einstein showed that Maxwell's equations of electromagnetism was not matching up with Galileo's principle of relativity. To understand this, we need to get a bit more acquainted with Maxwell's equations. The equations known as Maxwell's equations were not created by Maxwell. Maxwell simply compiled a list of experimental equations, and that list was a lot longer and a lot scarier looking than the set we know today. The set we know today was actually provided by Heavyset's simplification of Maxwell's compiled list. Inside two of the four field equations, Gauss's law and Ampere's law, there can be found two constants. The constant inside of Gauss's law is epsilon naught, which is called the permittivity of free space, which is the capability for an electric field to permeate a vacuum. There is also the permeability of free space, which is denoted mu naught, which can be seen appearing in Ampere's law, and is how permeable space is at letting magnetic fields flow through it. The permittivity value can be determined by using Coulomb's law, where the charges of two objects are known. The force between them is known, and the distance between the two charges is known. I have covered how Coulomb first found the value for the permittivity of free space in the History of Electricity video. We can just say that if two balls are given a charge of electricity, then they will exert a force on each other. The strength of the force will depend on the amount of charge and the distance between them. The constant that Coulomb used was necessary because the environment in which the charges interact makes a difference, even in a vacuum tube. The product of the charges, divided by the distance squared between them, is not the exact force. The permittivity is a constant of proportionality between the electric field in a material to the electric displacement in that material. And in this case, the material is the ether, or free space. You can have, as an example, the permittivity of water as well, which is not very permitting at all. If you take two metal plates and you charge one to be negative and the other to be positive, an electric field will form between the plates. If you place water between the plates, the electric field in between will decrease. If you remove the water and air between the plates, all that is left is the little stuff, which we find to have a constant property value of 8.854 times 10 to the negative 12 farads per meter. The permeability value is a proportionality between magnetic induction and a magnetizing force when forming a magnetic field. For example, the permeability of iron is very high, and will become magnetic in the presence of a magnetic field. Whereas wood has a very low permeability and can ignore the presence of a magnetic field. The wood is not permitting the magnetic field. The iron is permitting the magnetic field. The little stuff of the ether, or free space, has a property of permeability which is equal to about 4 pi times 10 to the negative 7 Henry per meter. Maxwell found that a time-varying electric field acts like a current and applies to Ampere's law, which says that a magnetic field is created. By applying this to Ampere's law, the equation becomes mu naught times epsilon naught times the time-varying electric field. This leads to a wave equation, and wave equations have waves which have velocity, and therefore Maxwell was able to find the speed of the electromagnetic wave, using only these two constants which are experimentally demonstrated. Maxwell found that the electromagnetic wave happens to travel at the same speed that light was being experimentally demonstrated to be, and was therefore able to link electromagnetism with optics, showing that light is in fact an electromagnetic wave. This explains why the tests of the speed of light through an ether demonstrated a constant speed of light, no matter the motion of the observer or the source. The wave speed of light is determined by the properties of the free space, or the ether if you prefer. Here then we can add that the constant velocity of light is the result of the electromagnetic properties of the ether. Maxwell's electrodynamics has a Galilean relativity problem as shown by Albert Einstein in the introduction of his 1905 paper on the electrodynamics of moving bodies. Let us explore this quickly using a simplified electromagnetic law, which states that an electromagnetic force is created by an electric force and/or a magnetic force. If a charged particle is displaced by this force, the displacement must be caused by one or the other, or a combination of the two. An electric force is caused by an electric field interacting with the electric field of the charged particle. A magnetic force is caused by an interaction between the magnetic fields. We know from the History of Electricity Lecture 2 video, a magnetic field will only exist around moving charged particles, and therefore the current creates a magnetic field, as does the moving test charged particle. A stationary charged particle does not cause a magnetic field, and therefore a stationary charged particle cannot interact with the current-carrying wire's magnetic field. Einstein used this law to prove that there is a Galilean relativity problem with Maxwell's equations. Paraphrasing Einstein, he writes, "A copper conducting wire has no built-in magnetic attraction, as the wire has an equal number of positive and negative charges, making the wire neutral. Maxwell's first equation, Gauss's law, says that an electric field depends on the charge density. A net charge would mean no electric field, which means no electric force. Even if we hook up a battery and get the electrons flowing, the charge density remains the same, and so there is still no electric field, and therefore no electric force." Maxwell's last equation, called Ampere's law, states that a moving current does create a magnetic field. The Lorentz force law states that an electromagnetic force exists if an electric field exists and/or if a charged particle is moving with a velocity through a magnetic field. We currently do not have an electric field present, but we do have a magnetic field now. But without a charged particle moving through it with its own magnetic field, there will be zero force. Here Einstein points out that the relative motion of the objects in the scene would violate either electromagnetism or Galilean relativity, both of which are experimentally confirmed to exist. so there must be something wrong with our interpretation. If we put a charged particle in motion near a copper wire, from the point of view of the stationary wire, a charged particle's magnetic field is moving through the wire's magnetic field, and, therefore, a force is created. But from the point of view of the charged particle, the wire is moving, and it is stationary, and so there is no velocity of the particle, which means there is no magnetic field for the charged particle, and the wire is neutral, so there is no electric field from the wire, and therefore there is no force whatsoever. From this point of view of an object moving relative to the charged particle, the laws of physics have changed, and Maxwell's equations would need to be rewritten, up until they stopped moving with the charged particle, where they would need to return to the old equations. This would mean that relativity wouldn't hold for objects in motion, which is the only reason for relativity to exist at all. Something is wrong here. When the observer is moving with the charged particle, there is still a force applied to the charge, yet in this frame of reference, there is no force generated by an interaction of magnetic fields as the charge is not moving, meaning the force can only be created from an electric field. The only way for an electric field to exist in this reference frame is if the charge density in the wire was not neutral. The only way to satisfy electrodynamics and the Galilean principle of relativity at the same time is if space and time are relative, as charge is invariant and does not change with respect to motion. This is where the concepts of length contraction and time dilation are implemented into the principle of relativity. The only way to account for the forces affecting the particle would be if the charges in the wire are no longer neutral, such that there is a higher density of particles of one kind or the other in the wire, which will depend on the point of view you observe the experiment. From the perspective of a stationary charged particle in the wire's magnetic field, the density charge would come from an increase in the protons in the wire. Assuming the wire is solidly packed with atoms that cannot move, this effect can only be true if the lengths of the proton have contracted. This would produce a high density of protons in that region, which produces an electric field, which would interact with the electric field of the stationary charged particle, and therefore an electric force interaction would occur. The solution to Maxwell's electrodynamic problem can therefore be solved using a special case of the principle of relativity, which leads us into Einstein's special relativity. This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you.